Welcome students. In today's module we are going to talk about one of the most important topics in C, which is dynamic memory allocation. So as part of this, at the end of this module, we should be able to understand about these 5 points. That is, first to begin with, we would like you to be able to distinguish between what is static and what is dynamic memory allocation, and then we will familiarize you with the functions that are actually used in order to carry out this dynamic memory allocation. And then as an example, we will try to allocate memory dynamically for a one-dimensional integer array, and then also as an example we will allocate and see how we dynamically allocate memory for a structure variable, and then finally we will see how we can allocate memory dynamically for a two-dimensional array. And at the same time I will also introduce to you some pointer notation using which we can actually access the members of the two-dimensional arrays and the one-dimensional array as well as the structure variables. First of all, you must understand what is memory allocation. In all your C programs, we have seen that we declare variables like this. We say that whenever you declare a variable like this, memory is allocated, sufficient memory is allocated in the random access memory so that an integer is able to be accommodated. For example, when you declare int a, in the memory, if you imagine memory to be a sequence of bytes, each box is a byte, integer a will allocate 2 bytes of memory, a minimum of 2 bytes of memory, because that will again change with machine to machine. Sometimes it can be 2 bytes, sometimes it can be 4 bytes also. But let us assume that in the given machine an integer occupies 2 bytes. So when you declare like this, memory is getting allocated like 2 bytes here. At the same time, when you declare like this, memory gets allocated somewhere, assuming a float takes 4 bytes. 4 bytes of memory is allocated in the random access memory so that when you enter a value, that value can be stored in this storage location or in this storage location if it is a floating point value. In order for you to understand the difference between static allocation and dynamic allocation, we have to be a little familiar with the process of compilation here, starting from the program that you write in C to the end at which the executable code is produced. As you all already know, C program is sent to the compiler and the output of that is the object code. It is passed on to the linker, and the linker joins the object code and the already existing library code and produces the executable code. This executable code, which is in machine readable format, is loaded into the computer memory and the CPU executes statement by statement. That is, whatever that you have to provide in a C program at this point is known as static. Once the program begins to execute, whatever values that you give, whatever occurs at the or during execution is known as dynamic. That is, to be more specific, all the values that you provide as input through the keyboard to the C program, which are read by the scanf statement, we say that all the such values are provided at runtime or at executable time to the program. So whatever occurs at that stage is referred to as dynamic. Whatever is given or provided at this stage is known as static. So if memory allocation occurs at this stage, it is static memory allocation, and if memory occurs at this stage, it is known as dynamic memory allocation. And all the declarations so far that we have learnt, they only allocate memory at this stage. That is, examples like all these: memory for a single variable, memory for the array, all that memory that you write, when you write in your C program, that memory, sufficient memory, is allocated at this time only. So these are all part of static memory allocation. Now we are going to look at dynamic memory allocation. One advantage of having dynamic memory allocation is you can always have an array of a size that you want. So there is a lot of flexibility that is available while using dynamic memory allocation, especially when you look at the programs that you are going to use in data structures, where data structures grow and shrink as the program executes. So we will be able to get memory as and when we require, and we are going to release memory if we don't want it. That kind of a flexibility is available here, which is not available here. There are three main functions that are usually used whenever we want to dynamically allocate memory in C. They are, namely, the name of the function is malloc, memory allocation, calloc, and free. These first two are used to allocate, and this function is used to deallocate memory. Now looking at the arguments for malloc, you simply have to provide how many number of bytes you want to be allocated as an integer number. 10 bytes, 20 bytes, 100 bytes, whatever number of bytes that you want to be allocated, that has to be provided within brackets. And upon being successfully able to allocate the memory, malloc will return a pointer which is of type void. Same way, another allocation function is there which is calloc, but it takes two arguments as you see here. First one is how many elements you want to be allocated, and the second argument is what is the size of the individual element. So if you give both, it will be able to calculate the total number of bytes that are required. It is going to allocate the memory, and it also returns a pointer which is of type void. But the main difference between malloc and calloc is that calloc will initialize all the bytes to zeros, and once you have finished using the memory that has been allocated dynamically, it's a good practice always to release the memory back to the system. Releasing part is very simply done by using the function free, free. In brackets we need to use a pointer which actually points to this allocated memory. That will be clear to you when we actually see an example. As an example, let us now look at how we can actually allocate dynamic fashion an integer array of any size. You can do that, but of course for the purpose of the example we will use size 5. Now, how do we statically allocate a one-dimensional integer array of size 5? We all know that this is how we declare. This statement here allocates an integer array with the name A of size 5. That is, we can store a maximum of 5 elements in this integer array. This is static allocation. Now I will just try to use a very simple program, C program, actual complete C code, wherein we will be able to allocate a dynamic array. Just read values into it and simply print back the values. So the idea of the program is simply to familiarize ourselves to the functions that are there which can be used for dynamic allocation, and once we have allocated the array, you will see that the usage of an array is exactly the same as if it has been statically allocated. There is no difference whatsoever in using the array once allocated, whether statically or dynamically. Whenever we have to use these dynamic memory allocation functions, we need to include one additional header file which is stdlib, standard library.h, and of course the usual stdio.h. This is what you have to remember. Now let us start the main function. I want now you to carefully look at the next line that I am going to write, which is going to make use of the malloc function. Malloc function name has to be taken in brackets. We need to provide the number of bytes. Now we know that we need to provide for n elements of the integer array. So we somehow need to calculate, we can make a calculation here which would give us the correct number of bytes that are required for the given number of n elements. So that can be done like this. N is the number of elements that you want multiplied by, because we already know we are going to use it for an integer array, we can get the size of each integer using the size of operator. This size of int will return either 2 bytes or 4 bytes depending on the machine. Let us now assume that size of int is only 2 bytes. Now assuming the value of n has been entered from the keyboard as 5, now you can very easily see what this entire expression calculates to, evaluates to. N is 5 multiplied by size of int. Assuming it returns 2 bytes, it will be 2. So totally the malloc's argument here would be evaluated to 10. So malloc will now allocate 10 bytes in memory. Somewhere in memory it will find 10 bytes, and this will return a void pointer to this block of memory. But we know that we are going to use this block of memory for integers, for the purpose of integers. So we need to cast this as an integer pointer in front. This has to be assigned to, so in total the statement is going to look like this, but I hope you are able to follow the order. Malloc function is there. For that argument we need to somehow calculate the correct number of bytes that you require depending on the purpose for which the block of memory is going to be used for. Here in this case we want to use the block for integers, so it has to be cast to integer pointer. Please notice that on the left hand side of the equal to sign you have p, which has already been declared as a pointer to integer. So this type and this type should match. So when you use malloc, you should have a pointer on the left hand side and you must cast it to the appropriate type, and in brackets here you must somehow calculate the number of bytes that are required for whatever you want. For example, in this case, in place of n it could have been 10, the value of n. The same statement here would have allocated 20 bytes, and a pointer is returned. That pointer will be stored in p now. So p, which is an integer pointer, would be pointing to the first byte of this block of 10 bytes of memory. So this is how the malloc function works. So once this has been allocated like this, then now there is no difference. Now this is equivalent to as if you have declared an array like this. Now let us see how to use this array. Now you have in your hand 10 bytes of memory, which are now going to be used as an array of 5 integers. Now all of us know how to deal with arrays using a for loop. You can simply go ahead and write like this. We all know this for loop will go through 5 times. Each time if you type in 5 values, the first value will go into p of 0, second value will go into p of 1, p2, p3 up to p4. Now instead of writing like this, we know we can also use a pointer notation. This and both are equivalent. That is, instead of ampersand p square brackets I closing the square brackets, you could have simply written after the comma here p plus I. Both are equivalent notation. Now having read it, you can very easily write one more for loop to print out the values that you have typed in. So that we can print out the values that you have typed in. The values could have been 10, 20, 25, 30, 35. Now instead of this notation, you can always use a pointer notation equivalent. You can try out when you write a program using this notation as well as this notation for printf. For scanf, we can use this notation or this notation. Always remember, for scanf we provide the address here, and whereas for the printf we simply provide the variable name. So these two are equivalent, these two are also equivalent. So with that you understand how malloc can be used malloc is a very simple function. It requires number of bytes. How to calculate, we have to decide as a programmer. Here, because we wanted an integer array, we calculated like this within the brackets here. That number of bytes are allocated. It returns a pointer which has to be cast to the appropriate type, and it has to be assigned to an appropriately already declared pointer. So just with this example, now we can go ahead and try to allocate a floating point array and just repeat the same program. Only changes will be appropriate places we need to change the data types. Everywhere else the program is going to be the, you can complete the program like this. Sometimes even if you miss the complete program, I request you to think of that and appropriately finish the braces so that we can write a complete program. Here this is a complete program anyway. A partially written program, you can see this is going to be used for allocating a node in a dynamic fashion and just use the members. Now the importance of this example is because the dynamic allocation of structure nodes are going to be used extensively in your later part of the course, that is data structures, where you have dynamic data structures which grow and shrink. We need to allocate nodes whenever we want. We would like to be able to delete nodes whenever we want, so on and so forth. So all that can be done and will be done using dynamic memory allocation. So this will help us to get a preview kind of thing before we actually get into the data structures part. So you can see that structure has already been defined. It is made to have a couple of members, an integer like we have done before, and a pointer which points to itself. So it's a self-referential structure, and type def has been used. So I will be using node in subsequent code. You can see here P is a pointer to type node, means that P can hold the address of a structure variable of type node. Now you remember how to use malloc. Malloc is the function. It requires number of bytes as an argument. What is the number of bytes that you want now? Sufficient to store one node. How do we know that? Do we know how many number of bytes this is going to occupy? Do we need to calculate that? No. We have the size of operator which automatically returns what is the number of bytes required for any given type. So we simply make use of size of. Mind you, here we are allocating not an array, just a single structure variable. Size of, you can simply say node. So the size of node will automatically return, the system will return the number of bytes required. That many bytes are allocated by malloc. But you know, now it has to be cast to the appropriate type. What is the type that I want to use? It is a node type. So you put node star here. This is called casting. Because malloc returns a void pointer, it has to be cast to the appropriate type of pointer equal to, you notice now P is type pointer, this and this P should match together. So this will automatically in the memory create, this will be your data, this is the next, which is a pointer, this would be pointed to by, notice that there is no name to this variable here. It is only, you can access this node only through this pointer because it does not have any name. All statically declared variables, they have names, whereas all dynamically allocated memory locations, they are accessible only through a pointer. That is one significant difference I would like all of you to notice. So that is the situation. We have a dynamically created node, structure node, now which is pointed to by P because of this dynamically allocated statement. Now we can simply, how do we use the members in this kind of a situation? Using the arrow notation. Now I can set value here, that will put 10 here, and I can just put whatever, I just put P cap, sorry, next will be assigned to null, which line will simply, so this is a very simple program. The idea of this program is very simple. It's not doing anything much except that it is telling us how to use malloc function to actually allocate sufficient memory for a structure node which is a self-referential. Of course, no matter what type of structure you can allocate, but I have taken the specific example because we are going to use this extensively in your data structures. So that will help you to understand. So the usage is same, malloc function, number of bytes in parentheses, cast to the appropriate type, having an appropriate pointer on the left hand side of the equal to. Automatically this will create a situation like this. Once this is done, we can go and use the memory through the pointer like this. Now let us try to understand how to allocate memory for a two-dimensional array, integer array. The notation will become a little complicated, but I am sure if you pay proper attention, you are able to follow what I am going to tell you. If you can understand this example, you will understand a great deal about pointers also. Let us start with a two-dimensional array of size 3 by 4. That is, you have 3 rows and you have 4 columns. We can visualize this 3 by 4 two-dimensional array as a sequence of 3 4-dimensional or 3 one-dimensional arrays of size 4. Is that clear? We can visualize the same thing as, let's split it up. Each one of these things is a one-dimensional array of size 4. How many such are there? 3. 3 by 4. And we already know that each one of these one-dimensional arrays can be pointed to by a pointers. That is, P is a pointer here, Q is a pointer, R is also a pointer of the appropriate type. P, Q are pointers now. And we can also put these 3 things in an array. And we can have another pointer which points to this array. We just have to progress from this idea to these one-dimensional arrays of integers, and ultimately this one-dimensional array of integer pointers which is again pointed to by m. At this point you must understand that m is, for example, if these are integer values, because this is pointing to integer, this will be a pointer to integer, int star, whereas m would be double star. That is, to get to this integer you have to come from here and from here to here. 2 levels of dereferencing is required. That is why m is referred to as a pointer to pointer, because this is an array of pointers, these are arrays of integers. So here you have int star, which points to that will be a pointer to pointer which is int star star. So this is the scheme. Now when we allocate, we come backwards. First we allocate this, then we allocate this array, then to each one of these pointers we allocate these one-dimensional arrays. First step is declaring m. Next step is allocating for this array. Mind it, it is an array of not integers but integer pointers. So how do we do that? Both should match, so it should be the same, followed by malloc, and inside we have 3 elements. What are the elements? Each element is an int star, so you say size of int star, close it. That will allocate m and this array. These are not allocated yet. Now we have to allocate 3 such integer arrays now, which will be pointed to by each one of these pointers. Actually now this will be referred to as m0, this element is referred to as m of 1, this element will be referred to as m of 2. Now we just go through a loop very simply, equal to 0, because we have to allocate equal to number of rows. So here the number of rows is 3, so otherwise it should be equal to rows. This is also number of rows. Again we say here you have to mind that at this stage we are allocating these arrays which will hold integers. So it's just like allocating our integer array in the previous example. So you see that size of int, sorry I missed something here, we need to know how many elements are there. So Here 4 elements are there, 4 times size of int. So in general case this should be number of columns. So what will malloc calculate now within bracket? Size of int, because you are allocating integers. How many such? 4. So 2 bytes, 4 into 2, 8 bytes will be allocated. A pointer will be returned, that is going to be cast to integer star, and it is going to be returned, and this notation you have to understand. What is m plus I? M plus I is simply, if this is m, this would be m plus 1, this would be m plus 2, because this address is m, plus 1 is the address of the next element, plus 2 would be the address of this element. But when you put star in front of m plus 1 or m plus 2, for example m plus 1 if you say, we are referring to the content of this box. Address is m plus 1, contents are star of m plus 1, which is a pointer. To that we are assigning the malloc whatever returns. For example, malloc allocates this array, sends a pointer to that. That is being stored here. And how do we refer to this contents of this location? M plus I. Of course, in the rotation it will start with I is equal to 0, it will be the first one. When I becomes 1, it will be m plus 1, then this is allocated. When I becomes 2, this is allocated, and m plus 2, it will be stored here. So just think about it a little bit. It is a bit complicated because we are dealing with pointers, addresses here, why we should star here, why int star here, why int here, why int star here, and int double star here. So if you spend a bit of time on that, definitely you are going to able to understand it. Now we'll simply take a very small example. Just once this is allocated, now this entire 2-dimensional array is allocated. We can simply, now let us consider this diagram here. M is the double star pointer to pointer, which is pointing to this 1-dimensional array, which is of pointers again, and each pointer is again in turn pointing to integer arrays like this. Now I want to access this element starting from m. I have m in my hand. Given this is referred to with 2 and 1. As you can see, it is in the second row and first, because all indices start from 0. So the index of this would be 2 and 1. Second row, first column. Now given m and 2 and 1, how do we get here? Quickly we look at it. To get there, first we have the address of this first element here. So I need to come here. That is m plus 1, m plus 2. So in order to come here, I simply add. That gives me a pointer to this box. But I need to get the contents here. How do I get the contents, which is nothing but the address of the first box here? Simply I put star in front. That will give me the address to this or this, both same. Once I have the address of this, I need to get here. If I know the address here, just go to the next element, which is simply plus 1. So this notation here gives me address of the required desired element. But if I want to access 99, the value at that address, all I have to do simply is, so you can notice here, this is the row number, this is the column number in this normal array notation. So just get used to this. It's quite looks complicated, but if you can think about it, taking a pointer, next stage and next stage, dereferencing, getting one pointer from the other, and ultimately going to an integer. If you can follow this process, I'm sure it's going to be not so difficult to use this pointers notation. Now what you can do is simply repeat what we did for 1-dimensional array. Using this notation, allocate 2-dimensional array, just read values into it and simply write back the values using the pointer notation as well as the normal array notation. Thank you.